This video is on valence electrons and something called the octet rule. So the first thing we're going to talk about is what is a valence electron, and then how do we count valence electrons. So from here on out in chemistry, valence electrons become our main topic of concern, so to speak, in terms of when we're talking about electrons. So up until this point, we've just been talking about electrons in general, and now we're going to make the distinction to something called valence, which is very important for the rest of our chemistry education. So what's a valence electron? Well, a valence electron is defined as electrons in the outermost energy level. Oh, I can't spell today. That is not how you spell energy. Energy level of an atom. Okay, so this is probably going to be familiar. We're going to backtrack a little bit in terms of talking about atomic structure and also presenting the structure of the atom probably from somewhere back in your science education. So maybe, I don't know, 7th or 8th grade, something like that, when you first learned about atoms. Okay, so I'm going to skip down here and I'm going to draw a picture for you because I think this is best presented like this. So if we talk about an atom, and so let's just say we have the nucleus. Okay, and we know, of course, that in the nucleus are the protons and the neutrons. But then at some point in your career, you've been taught that there are energy levels that surround the nucleus. And so there's something called the first energy level, and the second energy level, and the third energy level. And your previous science teacher may have even described them almost as orbits, like how planets orbit the sun. We're going to learn in chemistry that that's actually incorrect. But for a simplistic model, it does its job for our purposes now. So let's go ahead and label these. So this is the first energy level, and it can hold a maximum of 2 electrons. And as we start talking about this, you may start to remember this information. The second energy level is, of course, called the second energy level. And it has a maximum of 8 electrons. And then we have the third energy level. Depending on who your teacher was, they may have taught 8 or 18, and there's a reason for that. And we will kind of come back and talk about that in a little bit. There is a 4th, a 5th, a 6th, and the 7th energy level, but we don't really do a whole lot of discussing in there only because those start to become very large atoms, and it would take a long time for us to draw those pictures. So let's talk about lithium, for example. So I'm going to put that this is lithium, okay? So if we think about lithium, I'm going to, for now, ignore protons and neutrons just to make this discussion easier because we're focused on the electron. So if I look at my periodic table, I know that lithium's atomic number is 3. So 3 protons, and assuming this is an atom, no charge, it also has 3 electrons. So if I'm going to place these 3 electrons, 2 of them would go in the first energy level, because the first energy level can hold 2. And when I go to place my third electron, it must go in the second energy level because the first energy level was full. So you probably have drawn pictures like this in previous science classes where you built models of the atom and placed these electrons in their proper energy level. And that still holds value in this topic of discussion on something called valence electrons. So let's get into that now. So looking at this picture, I know that there are 3 electrons in my picture, right? I have 2 in the first level and 1 in the second. So I'll write that down. I have a total electrons. There are 3. But now, what I'm interested in learning about are these things called valence electrons. And valence electrons, we'll go back up to our definition, are electrons in the outermost energy level of the atom. So for lithium's outermost energy level is level 2 because it's the highest level with an electron in it. Now you might be saying, well, level 3, right, is higher than level 2, but there are no electrons there. So valence electrons the highest energy level is the highest energy level with electrons in it. Okay, so for lithium, in level 2, there's only one electron. So that one electron becomes termed the valence electron. So lithium has one valence electron. It resides in level 2. So if this is a valence, that means these two cannot be valence. They have to have another name. And that other name is core electron. So we might want to add that somewhere. Maybe we have room up here that a core electron, or your electrons that aren't on the highest energy level, that's exactly what they are. Electrons not in highest energy level. We sometimes refer to them as the inside electrons. Okay. So in this case, lithium has 2 core electrons. So we're going to come up with this little math equation. It's a very simple one, but the math equation says valence plus core make total. So that's important to us. Okay, so valence plus core make total. Okay, so now I drew this little periodic table up here because I want to keep track of valence electrons, and I want to do that for a reason. So I'm going to label this valence electron. And I learned that lithium, who resides right here, has 1 valence electron. So I put a little 1. Okay, so because I'm on this iPad and it's easy to do, let's amend my picture here. And I'm going to get rid of these just to clean this picture up a little bit, now that we've already identified the energy levels. And okay, there we go. That's better. All right, so let's amend this picture, and let's say that instead of helium, let's do the one that, instead of lithium, that this is beryllium. Okay, so it's the next one in line. I started with lithium. So beryllium has 4 protons, so 4 electrons. So 2 electrons in the first energy level, they're already there, and 2 electrons in the second energy level. And this would be beryllium's picture. So let's do our kind of math here. So total electrons, we know beryllium has 4. Valence electrons are these 2 in the second energy level, so 2. And then the electrons in the first energy level are the core, so 2. Again, my math works. Valence plus core, 2 plus 2 gives me 4. So beryllium, has 2 valence electrons. I didn't give myself a whole lot of room, but that's okay. All right, onward. So let's change to, who comes next? Boron. So let's say this is boron. Oh my goodness. So boron has 5 protons, so 5 electrons total, 2 in the first level, and this time 3 in the second. Remember, the second level can hold up to 8, so I can keep filling it. So if I do my little box here as I'm kind of going through these, beryllium has a total of 5 electrons. Valence electrons are 3 because the second level is my outer level, and core electrons are still 2. Again, 2 plus 3 gives me 5. So filling in my little chart, boron, who's over here, has 3 valence. Are you sensing a pattern? Can you see we're going to a pattern here? Okay, so next would be carbon. So if we do carbon next, carbon has 6 protons in the nucleus, so 6 electrons, 2 in the first level and 4 in the second level. So total electrons would be 6. Valence electrons would be 4, right? The 4 in the second level. Core electrons still 2. Notice the core electrons have not changed so far. So carbon, who resides here, has 4 valence. Keeping on this path with our pattern would be nitrogen. So nitrogen has a total of, I lost my train of thought. I'm sorry. 7 protons, 7 electrons, 2 in the first level, 5 in the second level. So 7 total, 5 valence, 2 still are core. So, oh my gosh, lithium. Nitrogen has 5 valence electrons. Onward, Oxygen comes next in this discussion. Oxygen has 8 protons in the nucleus, 8 electrons total, 2 in the first, 6 in the second, 8 total electrons, 6 valence, and 2 core. So filling in my table, oxygen has 6 valence electrons. Okay, we're almost there. With fluorine, 9 protons in the nucleus, 9 electrons total, 2 in the first level, 7 in the second level, making 7 valence, 2 core. So filling in my valence, fluorine with 7, and last but not least across this period of the table would be neon. 10 protons in the nucleus, 10 electrons, 2 in the first level, 8 in the second level, 10 electrons total, 8 valence, 2 core, and we finally round out my period of the table. So I'm sure you can sense a pattern, excuse me, in this table, my valence electrons are increasing by 1 as I go across the table. Let's see what happens when I jump down and do my next row, which is sodium. So sodium has 11 protons, 11 total electrons, 2 in the first level, 8 in the second level, and I have 1 more to place, but my second level is full, so that electron must go into the third level. So watch what happens now. Valence electrons, 1, it's this guy right here, 1 valence electron. How many cores? Everything else. So what has happened now are my core levels are not only level 1, but also level 2, because level 3 is the outer energy level. Okay, so in this case, core electrons are in levels 1 and levels 2. So I have a total of 10 core. Again, you can check it. 10 core plus 1 valence gives you 11 total, which we know has to be true. So look what has just happened to my pattern. Sodium, who resides under lithium in the table, also has 1 valence. If we were to do one more, who is magnesium, I believe, comes next. Magnesium has 12 protons, 12 total electrons, 2 in the first, 8 in the second, and then I have 2 more that I need to place. So there's the 1 and there's the second one, 2 in the third level. Valence electrons, these 2 right here. Everything else is a core. So 10 core, 2 valence. That's what I wanted to do. Magnesium also has 2. So I'm sure now you can sense that there's a pattern that not only develops left to right in the periodic table, but also up and down within the groups. Okay, and that pattern is this. I refer to it as a shortcut for valence electrons. Everyone in group 1 has 1 valence electron. So hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. They all have 1 valence electron. They have different numbers of core electrons, but they all have 1 valence. Everybody in group 2 has 2 valence. Okay, everybody, no exceptions. Now, when I get to the middle section, my transition metals, which reside here, for right now, I'm going to put a question mark because the deal here is that while they don't have 0 valence electrons, that doesn't make any sense. Everybody has some number of valence electrons. They just unfortunately don't follow this pattern that is so easy to see. Okay, so for now, we're going to leave that as a question mark and we will revisit that discussion later. So everybody in group 13, starting with boron and aluminum, they all have 3 valence. Carbon's group have 4 valence. Nitrogen's group has 5 valence. Oxygen's group has 6 valence. Fluorine's 7, and my noble gases with 8. There is only one exception to this rule. And that one exception is helium. And I'll show you why. If you think about it, helium has 2 protons. So 2 protons means 2 electrons. So 1 electron, 2 electron. Okay. So his first level is full. And so if I think about how many valence, well, in this case, the valence is my first level electrons. So helium has 2 valence. He's the only one on this whole table who is the exception to this rule, okay? Because there's no way helium could have 8 valence electrons. Helium doesn't even have 8 total electrons. So helium has 2. Now, what becomes an interesting question is why then is helium placed here instead of over here? Maybe some of you know the answer, maybe some of you don't, but it's definitely a topic of discussion for us, just not in this video, okay? So valence electrons become of utmost importance to us, learning how to count them. And the beautiful thing now is that you don't have to draw a picture. You can just use your shortcut that we have labeled here. So, for instance, if we're going to talk about barium, okay? Barium's way down here in the table. Atomic number 56. I don't know about you, but I don't want to draw my picture with energy levels and 56 electrons. And there's no need to do it, and I'll show you why. Because with barium, how many total electrons? These are the questions you should be able to answer at the end of this video today. Okay, so barium total electrons, well, it has 56 electrons because it also has 56 protons. Valence electrons, I can use my shortcut tool. Barium resides in group 2, which means barium is going to have 2 valence electrons. I can even throw in how many core electrons, because you should know if there are 56 total and only 2 are valence, that means 54 of them must be core electrons. And those are the 3 types of electrons you should be able to count at the end of this discussion. Okay, remember, valence plus core equals total every time, no exceptions. Okay, this is a big takeaway point. If I take my valence and my core, I will always get total electrons. Okay, only one more topic in today's discussion, and that is the topic of the octet rule. Oops, as you might have guessed, octet or oct is a prefix that means 8. So the octet rule has something to do with the number 8. And the octet rule says this. And this is also a very big deal. So the octet rule says that all atoms are stable when they acquire or when they already have 8 valence electrons. So if we go back up here to our shortcut, okay, who on the table has 8 valence electrons? Well, only the noble gases. So according to the octet rule, only the noble gases are stable as is right now, according to the table. Everybody else is unstable, and so they have a goal, and here is one of the biggest takeaways in chemistry. The goal is for atoms to acquire 8 valence electrons to achieve stability. Now, how do they do it? How do they acquire 8 valence electrons? That is a huge topic. It's our next topic of discussion, but how they acquire them is they either gain or lose valence electrons. So it seems relatively easy enough to state that that's how they acquire them, but what really happens when atoms gain or lose electrons to come up with 8 valence